Okay, good evening, everyone. So,
good evening, sir.
Good evening. So, let's begin our lecture for today. So, we are in the basics of finite difference method. And then we said in the yesterday's lecture that whenever you have a let us say a finite difference mesh, what we have created yesterday was a Cartesian mesh, okay, which has some intervals. And then we said when you are closer to the boundaries, you have only points only on one side of the domain. Let us say if you are on a boundary, then you have only points on one side of the domain. Let us say if this is I, you only have I plus 1, I plus 2, I plus 3, and so on, only on this side. Similarly, if you're on a boundary that is on the right-hand side, then you have only points that are like this. For example, this is, let us say, I, then you have I minus 1, I minus 2, I minus 3, and so on. Whereas when you are in the interior of the domain, then you have points on both sides. If you are on at a point, then you have I plus 1, I minus 1, and so on, right? So all these points are available. So as a result, we would be working with one-sided schemes near the boundaries, or we'll be using one-sided schemes which take into account only either I plus 1, I plus 2, and so on near the boundaries. And we're going to use central schemes which make use of I plus or minus 1, I plus or minus 2, and so on when we are in the interior. Of the domain. Okay. Now, yesterday we just started deriving the formulae. So we said if you want to calculate what is partial u by partial x at any point I, we said we could get this using Taylor series expansion. So we wrote essentially, we expanded ui plus 1 as about ui as ui plus delta x times partial u partial xi plus delta x square by 2 factorial partial square u by partial x square plus delta x cube by 3 factorial partial cube x by u by partial x cube at I, and so on, right? Instead of delta x, we might have used h, meaning this is the grid spacing. Okay. Now, what we said was, if we were to calculate what is partial u partial x from here, we said partial u partial x at the point I equals ui plus 1 minus ui divided by delta x, plus or minus, we have order delta x terms. And because we are going to approximate this partial u partial x as simply ui plus 1 minus ui by delta x, we are going to neglect this term, right? So as a result, we call this thing as the truncation error as applied to this particular scheme, right? And then we also said that this particular truncation error, which is the leading order error, which is the highest error that we are truncating out of the entire series, because other things have delta x squared, delta x cube, and so on. These are not large because we are talking about delta x to be less than 1. Okay, if that is the case, delta x squared, delta x cube, and so on are going to be much smaller compared to delta x. So as a result, the lowest order term which we are neglecting in the entire series is going to be the leading order term. So essentially the lowest power of delta x term will be the leading order term. Okay, so that's what we said. Then essentially this is going to be, because in the terms that we are neglecting, it is ordered to delta x to the power 1. So this is basically this particular method when we write dou u dou x at I equals ui plus 1 minus ui divided by delta x is known as first order accurate. Okay, which basically means that if you are going to make your delta x to delta x by 2, then your truncation error, whatever you have, is going to become truncation error by 2, right? Because it's only going to become half of, or essentially it's going to go down only with delta x to the power 1. Okay, so your truncation error basically gives you a sense for what is the error in a relative sense. So it basically gives you the error involved in a relative sense, right? So I will not know what is the absolute value of the error because I am given a function u of x. I am only calculating what is dou u dou x at a particular point I. But then if I refine the mesh, if I make it instead of h, if I take h by 2, I know that the truncation is going to go down by half. So it's only going to give error in a relative sense, not in an absolute sense. So to know the error in an absolute sense, we still have to compare it with. We still have to compare it with the exact answer if we know. Okay, otherwise we won't be able to know it. Okay, but then nonetheless, truncation error gives a sense in a relative sense what is the error involved. Now, as we said, the first order accurate formula which we have derived here is essentially is 2 cores. So this is 2 cores. That means it is only first order accurate. So to be used in general computing. Okay, so we will most likely not be using such a simple first order accurate formulas. We would need higher order accurate formulas because otherwise the truncation errors involved are large. Okay, so we won't be able to get meaningful correct answers with that. So then let us try to derive a first order accurate formula, first order derivative to second order accuracy. Okay. Now, this essentially calls for us to include more points. That means more points, because earlier we have only used the points I and I plus 1. So this formula only makes use of I and I plus 1. So we can call this as a forward difference formula. This is a forward difference. Okay, because we are talking about at the grid point I, we're using I and I plus 1. So this is a forward difference, or FD, okay, formula. Now let us try to derive a first order derivative. That is, still we want to derive dou u dou x at the point I to second order accuracy. That means we want to derive it to delta x square accuracy. Okay, and then let us still make use of forward differences. Okay, that means we are still deriving one-sided difference. That means let us include the points instead of just I. Let us also include I plus 1 and I plus 2. So earlier we were only including I and I plus 1. Now let me include one more point so that we can derive higher order accurate, second order accurate formula. So if that is the case, that means we have our grid. Let us say this is I, this is I plus 1, this is I plus 2, and I plus 3, and then we have some values of ui plus 1, ui plus 2, and so on. Okay, that means if I were to derive what is this is ui plus 1, ui plus 2, and so on. So I can, just like before, let me write ui plus 1, which is the value of u at xi plus 1 using Taylor series expansion. So we are again using Taylor series expansion, and I'm going to write this as ui plus h times partial u by partial x at I plus h square by 2 factorial partial square u by partial x square at I plus h cube by 3 factorial partial cube u by partial x cube at I plus, and so on. Okay. And then we have, let me make use of ui plus 2. Now ui plus 2, that means what we have done is we have expanded ui plus 1, which is this value about ui, right? So we are expanding about ui. Similarly, now I want to expand what is ui plus 2 about ui. Okay, so again I want to expand about ui. That means here we notice that the distance earlier involved was h, whereas for ui plus 2 the distance is 2h, right? Because it is 2 grid points away. But then I want to still expand it about ui or xi. Actually, I want to expand it about xi, not ui. So that's going to be a value of ui plus 2h times partial u by partial x at I plus 2h square by 2 factorial partial square u by partial x square at I plus 2h cube by 3 factorial partial cube u by partial u at I, and so on, right? That's what we have. Now, I have two equations, first equation and second equation. Now, I want to combine, so essentially combine equations 1 and 2 such that we are going to get a formula for dou u by dou x at I to second order accuracy, right? That is our objective. Now, to do this, let me, in general, so earlier it was easy because I just had only one term. We expanded about ui plus 1, and then we could just take this to the left-hand side and then obtain an expression for this dou u by dou x at I, right? Now I have little more complication. So what I will do is that a general method is to basically multiply the first equation with some parameter alpha, the second equation with some parameter beta, and then see what is the resulting expression. Okay, and then we will set certain conditions such that we're going to derive what is dou u by dou x at I to whatever is the maximum possible order of accuracy, or the order of accuracy that is given is delta x squared. Okay, so I'm essentially multiplying first equation with alpha, second equation with beta. Okay, and then expanding it out. That means on the left hand side, when I multiply this first equation with alpha, then the second equation with beta, okay, and then sum them up on individually on both left and right hand side. So we have alpha times ui plus 1 plus beta times ui plus 2, that is what I have on the left hand side, equals ui times, this is going to be alpha plus beta, right? Because you have ui times alpha plus beta. Then the next would be h times dou u by dou x times, so this is going to be h times dou u by dou x at I times, the first equation will have alpha, this will have alpha, this will basically be 2 beta, right? This is basically going to be alpha plus 2 beta when you sum them. Okay, similarly, the third equation is going to be h square by 2 factorial dou square u by dou x square I. So this is going to be h square by, h square by 2 factorial times dou square u by dou x square at I times alpha going to come from the first equation. Then this equation is going to be 4 times beta, right? Because we have 2h square, so it's going to be plus 4 beta, and then plus h cube by 3 factorial times partial cube u by partial x cube at I times, we have alpha plus 8 beta, right? So we have alpha plus 8 beta and so on, right? That is what I have. So this is the equation that has combined your ui plus 1 and ui plus 2 equations as such. Now, now the thing is that now I want to calculate what are the values of alpha and beta, such that I'm going to get second derivative dou square u by dou x square at I to first derivative, that is dou u by dou x at I equal to second order accuracy, right? That's what I want to do. So what that means is that now if I look at the first derivative, so this is where the first derivative is. And then I don't want any higher order derivatives to be there in this problem, right? That means I don't want to include, let us say, higher order derivatives, because I want to calculate this one. But then I still need two equations because I have two unknowns to calculate, right? So what I do is that I want to keep this term, but then I want to make this coefficient that is there as 1. And I don't want to keep any dou square u by dou x square. So I want to make this coefficient of this to be equal to 0. That means I want to set alpha plus 2 beta times h equal to 1, so that I'm going to get an expression for dou u by dou x at I. This is the only dou u by dou x term in the entire equation. Okay. Similarly, on the right hand side, I have this term, which is second derivative, and I don't want any higher derivatives to appear in the equation. So as a result, I'm going to set this alpha plus 4 beta times h square by 2 factorial equal to 0, right? So that's what we said. We don't need to set anything here because this is going to be there anyway, and then we only need the first two terms, right? Because I want to achieve second order accuracy, essentially this will become h cube, right? So this is basically h cube, but when I'm going to divide that with this h to calculate dou u dou x, this is going to become order h square, and I can neglect this term in the truncation error. So I'm only, and then I essentially don't want to include this term, because if I include this term, this is a h square, but then when I divide with this h, this term is going to become order h term, right? Which I don't want, because I want to derive dou u dou x at I to order h square. So I don't want any second derivative or h square terms in here, because they will become first order accurate when I try to calculate, when I divide with h. Okay, so that's the reason I'm kind of setting this coefficient equal to 0. Okay, then I can, from here, I can say that my alpha equals minus 4 beta from the second equation. If that is the case, I can go back and substitute this in the first equation, which is going to give me minus 2 beta equals 1 by h. That means beta equals minus 1 by 2h. If beta equals 1 by 2, minus 1 by 2h, my alpha is going to be 2 by h, right? Because that is equal to minus 4 beta, that is minus 4 times 2 by h is going to be plus 2 by h. Okay, so that is what I got. I got alpha equals 2 by h, beta equals minus 2 by h. That means I'm going to go back and then substitute for alpha and beta into this equation. Okay, then it's going to give me alpha times ui plus 1, that is 2 by h times ui plus 1, plus beta times, that is minus 1 by 2h times ui plus 2 equals, on the right hand side, I have ui times alpha plus beta. So this is going to be ui times alpha is 2 by h minus ui plus beta. This is minus 1 by 2h. Okay, that's what I have. And then this term, h times alpha plus 2 beta, I made it 1. So this term is going to become plus dou u by dou x at I, plus this term, I made it 0. So as a result, this term is not there. And then this term is going to be h cubed divided by h, right? So this is going to be just h square, right? Essentially, this is going to be h square. Okay, this is order h square, right? Okay, so that's what I have. Then what would be my dou u dou x? Dou u dou x at I is going to be, I can write here, this is going to be minus 1 by 2h ui plus 2 plus 2 by h ui plus 1 minus ui times, this is going to be 2h. If you take it out common, then this is going to be 4 minus 1, 3. So this is going to be 3 by 2h, right? That means I can write this as minus ui plus 2 plus 4 ui plus 1 minus 3 ui divided by 2h plus order h square. Okay, that is dou u by dou x at I. So that is the first order accurate formula. Sorry, this is the first derivative to second order accuracy, right? So we have just derived what is the formula for first derivative, which is basically the forward difference formula. So the forward difference formula for first derivative to second order accuracy. Okay. Any questions so far on how we are deriving this?
No, sir. Like we will review and get back to you, sir.
Okay, fine, all right. So then, so that is about calculating first derivative forward difference formula. Let us see now. In a similar way, you can also calculate what is backward difference formula. Okay, That means if you want to calculate a derivative at I, you can involve I minus 1, I minus 2, I minus 3, and so on, right? All these can be implemented. Then what we see is that in general, if we want to calculate, let's say, rth derivative to mth order accuracy, okay, then in general, you would require r plus m points, including the ith point. Now, what does this mean? Essentially, let us say we have seen, we wanted to calculate dou u dou x at I to first order accuracy. That means your r equals 1, that is the rth derivative, m equals 1. Then we needed r plus m 2 points because we used I and I plus 1, right? This is true for all the forward differences and backward differences. Similarly, when we wanted to calculate dou u by dou x at I to second order accuracy, we have r equals 1, m equals 2. We used 3 points. That means we ended up with I plus 1, and I plus 2, as in this formula, right, where we have I plus 1 and I plus 2 to calculate up to second order accuracy. Okay, fine. So this basically gives us how many points we need. So the points on where the function is required is known as the stencil of the scheme. Okay, as you can see, as you wish for higher and higher order of accuracy, as you increase delta x n, the size of the stencil increases. Right? That means if you want to have, let us say, first derivative to fifth order accuracy, then essentially r plus 1 will be 6. Then you would require I plus 1, and so on, all the way to I plus 5, right? So you need more and more points so that the size of the stencil will increase if you want a higher order accurate scheme. Okay, so this is true for both forward differences and backward differences, and also for central differences in general. Okay, so now let us try to derive a backward difference formula for second derivative. Let's try to derive a backward difference formula. For second derivative, dou square u by dou a square at I to second order accuracy. Okay, we want to derive this thing. Okay, then how many points do I need? My r equals 2, my m equals also 2, so my r plus m equals 3. That means, r plus m equals 4. That means I would need I, but then I want to go in backward difference, so it's going to be I minus 1, I minus 2, and I minus 3. Right? That's all. These are the points I would like to. So my stencil, my scheme depends on the stencil, right? Stencil for the scheme is I minus 1, I minus 2, and I minus 3. We need function values at these points in order to be able to calculate the second derivative to second order accuracy. Okay, then just like before, we are going to write what is ui minus 1. Ui minus 1 is going to be, because now there is a minus, so we need to be careful with the Taylor series expansion. It's going to be ui minus h times dou u by dou x at I plus h square by 2 factorial dou square u by dou x square at I minus h cube by 3 factorial dou cube u by dou x cube at I plus h power 4 by 4 factorial 4 by partial x power 4 at I, and so on, right? That's what we would get. Similarly, I'm going to get ui minus 2 equals ui minus, this is going to be 2h partial u by partial at xi plus this is going to be 4h square by 2 dou square u by dou x square at I minus this is going to be 2h cube, that's going to be 8h cube by 6 partial cube u by partial x cube at I plus this is going to be 16h power 4 divided by 24 partial 4u by partial x power 4i, and so on, right? That's what we're going to get. Then ui minus 3 would be ui, right, minus 3h partial u by partial x at I, plus this is going to be 9h square by 2 partial square u by partial x square at I. Then we're going to get minus So this is going to be 27 h cubed by 6 partial cube u by partial x cubed at I, plus this is going to be 3 to the power 4, that is 81 h power 4 by 24, 4u by partial x power 4I, and so on. Okay, so we got all these points. Now, just like before, now I need to essentially come up with a combination of this such that we're going to get second derivative to second order accuracy. Okay, so that means I'm going to multiply. Let us say if I were to call these equations as this is the first equation, this is second equation, this is the third equation, then I can write again just like before, multiply first equation with alpha, second equation with beta, and then the third equation with gamma, and then equate, and then set the terms which we don't want it to be 0 and then which we want it to be 1, and so on, so that we can derive what is alpha, beta, and gamma. Okay, that's going to be alpha times ui minus 1 plus beta times ui minus 2 plus gamma times ui minus 3 equals, on the right hand side, first term is ui, so that's going to be ui times alpha plus beta plus gamma. Then we have minus h times dou u dou x. This is going to be h times partial u partial x and I times what we have is the value is 1 here, 1 plus, that means alpha plus 2 beta plus 3 gamma. Okay, that's what these are going to be. Then we have plus h squared by 2 dou square u by dou x square. That means plus h squared by 2 dou square u by dou x square at I times what we have is again, this is going to be alpha, this is going to be 4 beta, this is going to be 9 gamma, right? Because I have taken h squared by 2 common. So it's going to be alpha plus 4 beta plus 9 gamma. Okay. Then I have minus h cubed by 6 partial cube by partial x cube I times. So this is going to be essentially 1. This is going to be alpha. This is 8 beta and this is 27 gamma. So this is alpha 8 beta 27 gamma. Okay. Plus we have order h power 4 terms, right? That's what I have. So because this is second derivative, I can kind of neglect, I mean, essentially this is going to be second order accuracy is what we want. So order h power 4 by h square will basically give me order h square. So I'm not writing these terms here. Okay. And on top of that, we have only 3 free parameters, that is alpha, beta, and gamma. And I would need these three parameters to be calculated from 1, 2, and 3 equations as I have, right? That means I want to calculate dou square u by dou x square times, I want to set this term to 1, and this is the coefficient of dou square u by dou x square equal to 1. Okay, that is one equation I would get. And then I don't want any terms of h cube, because h cube when divided with h square is going to give me order h terms. So I don't want any of these terms. And similarly, I don't want any first derivatives, right? Because these are also, I'm not looking for a first derivative as such. So I want only in terms of second derivative. Okay. That means I can write this as this is alpha plus 2 beta plus 3 gamma times h equals 0. That is one constraint I have. Second one is alpha plus 4 beta plus 9 gamma times h square by 2 equals 1. Okay, that is the other constraint I'm putting. And then the last constraint is basically alpha plus 8 beta plus 27 gamma times h cubed by 6 equals 0. Okay, the h can be neglected from here because it's anyway 0 on the right hand side. Okay, so I have these things. That means if I were to, so essentially I now ended up with a system of equations, right? Only thing is that now I can write them in terms of a matrix form. So it's going to be 1, 2, 3, 1, 4, 9, 1, 8, 27, right? Times what we have is alpha, beta, gamma equals 0, 2 by h square and 0, right? Essentially this term, if it goes to right hand side, it will become 2 by h square. Okay, so this is the system I need to solve. Okay, so I'll resort to my Gaussian elimination. I'll say R2 tends to R2 minus R1, R3 tends to R3 minus R1. So that's going to give me 1, 2, 3, 0. This is going to be 1 minus 1, 0, 4 minus 2, 2, 9 minus 3, 6, 2 by h square. Okay, And then the last row, R3 is going to be 1 minus 1, 0, 8 minus 2, 6, 27 minus 3, 24. And this is going to be 0 minus 0, 0. Okay, that's what I have. Fine. So I quickly reduced it to upper triangular. I just need to do one more iteration. So that means R2 is the pivot row. So I can say R3 tends to R3 minus 3 times R2. Okay, that's basically going to give me 1, 2, 3, 0. This is going to be 0, 2, 6, 2 by h square. Then this is going to be 0 minus 0, 6 minus 6, 0, 24 minus 18, that is 6, right? And then you have 0 minus 6 h square. So this is going to be minus 6 by h square, right? That's what I have. That means now it is in upper triangular form. So this is already in upper triangular form. I can solve for this thing. So that means 6 times gamma equals minus 6 by h square. That means gamma equals minus 1 by h square, right? That's what I got. Okay. Then similarly, from the second equation, we have 2 times beta plus 6 times gamma equals 2 by h square. That means 2 beta equals 2 by h square minus 6 gamma. That is going to be plus 6 by h square. This is 8 by h square. That means beta equals 4 by h square. Similarly, for the first equation, we have alpha plus 2 beta plus 3 gamma equals 0. So we have alpha plus 2 beta plus 3 gamma equals 0. So that means alpha equals minus 2 beta minus 3 gamma. So this is minus 8 by h square minus 3 gamma would be plus 3 by h square minus 5 by h square. Okay. Is this correct? Okay, let's see. So we got alpha, beta, beta and gamma. Okay, so then I can go back and then substitute into this equation. So on the left hand side, what I have is alpha plus beta plus gamma. Okay, so that is going to be alpha times ui minus 1 plus, so essentially, yeah, that's what I have. So alpha times ui minus 1. So this is minus 5 by h square ui minus 1 plus beta plus 4 by h square times ui minus 2. And then I have plus gamma, that is minus 1 by h square times ui minus 3 equals, on the right hand side, I have alpha plus beta plus gamma, alpha plus beta plus gamma times ui. Okay. That means what I have is ui times alpha plus beta by gamma, that is minus 5 by h square plus 4 by h square minus 1 by h square. Okay. Then the next term, this term is 0. We set this equal to 0. And this term is actually equal to 1 times dou square u by dou x square. And this time equals 0. And then this is order h square. So what I have is I have plus dou square u by dou x square at I plus order h square, right? That's what I have. Okay, that means I can now write my dou square u by dou x square at I to second order accuracy as, how much will this be? This will be minus 4 plus 3. This is going to be minus 2 by h square. Okay, so that's going to be minus or 2 ui minus 5 ui minus 1 plus 4 ui minus 2 minus ui minus 3 divided by h square. 6 minus 6. Okay, this seems to be correct. 6 minus 3 plus 3. Yeah, I think this seems to be correct. There are no mistakes. Okay, so this is the plus order h square, right? So this is the backward difference formula. So this is backward difference for second derivative to second order accuracy. Okay. So that is how you can derive any final difference formula. Of course, you can also write a program to derive this coefficients, right? Even this scheme can be derived using a program. So you can even make a program like that, because all you're doing is basically formulating this. So there is a clearly a pattern, right? With this pattern, we can easily write a program which will solve for these things. And then if you type in, let us say, I want to derive this formula, you will be able to derive that, right? Through the pattern name. Essentially, you just need alpha, beta, gamma, and then you'll be able to plug it in. So that can be done. But anyway, we will not worry about that at the moment. For the purpose of the course, we are going to derive these formulae by hand like this, okay, by using Taylor series expansion and then matching the coefficients like this. Okay, so of course you can go on deriving this thing. Now instead of that, let us look at how do you come up with final difference formulae for the interior points. That is, how do you calculate the central difference schemes? Central differencing schemes. These are for the interior points. Okay. So let us try to derive maybe a central difference formula for first derivative. That is dou u by dou x at I. Let us derive CD or CDS, central difference scheme, to first order accuracy. Let us say we want to derive to first order accuracy or to second order accuracy. Okay, to second order accuracy is we want to derive. So that means I need to basically look at the derivative is R and the order of accuracy is 2. So I'm basically required 3 points, but then the stencil is symmetric, right? The stencil is symmetric. So this is going to be I plus 1, and then I minus 1, right? I would need to calculate U at all these 3 points, right? That means I will write a formula for Ui minus 1. Ui minus 1 is going to be Ui minus h times partial U by partial x at I plus h square by 2 factorial partial square U by partial x square at I minus h cube by 3 factorial partial cube U by partial x cube at I, and so on, right? Similarly, Ui plus 1 is going to be Ui plus h times partial U by partial x at I plus h square by 2 factorial partial square U by partial x square at I minus h cube by 3 factorial partial cube U by plus I, and so on. Okay, so this is plus. All are plus for the I plus 1. Okay, so I have these 3, but then here it is much more straightforward because we just need to calculate for dou u by dou x, right? So that means I have the first equation and the second equation. We actually don't have to multiply with alpha and beta and do all that analysis, because here it is straightforward. I can simply subtract off one equation from the other. I can probably subtract off first equation from the second equation, and this is going to be Ui plus 1 minus Ui minus 1 is going to be, this is going to basically become 0, Ui minus Ui. This is going to be 2h times dou u by dou x at I. And then again, this term is going to be 0, right? This is 0. And then this term will basically become 2 times h cube by 6, right? Dou cube u by dou x cube at I. Right, that's what it is going to become. That means if I want to calculate what is dou u dou x at I, this is going to be Ui plus 1 minus Ui minus 1 divided by 2h plus order h square, right? So this is the central difference formula for the first derivative to second order accuracy. Okay. Again, this is very straightforward, just like the way we have done before. Okay, then similarly, I can also derive the central difference formula for second derivative, dou square u by dou x square at I to second order accuracy. Okay, that means my R equals 2. My m equals 2, so my R plus m equals 4, right? But then we realize that because of the symmetry, that is involved, that means you're taking points from both sides, we could get away with just 3 points. Okay, by involving just 3 points, we don't need the 4th point, and this is true for all even derivative calculations. On even derivative calculations for central difference schemes. Okay, so when you want to calculate even derivative using central difference schemes, then you can get away with 1 point lesser. That means you just need r plus m minus 1 points as your stencil. Okay, when you apply central difference scheme, if r is even, Okay, so if r is even, then what we want is this. Okay, what we need is this thing. Okay, so to do this again, let me write down what we have done before. Ui minus 1 equals ui minus h times partial u by partial x at I plus h square by 2 u by x square minus h cube by 6 q by x cube plus h power 4 by 24 4u by x4, right? That's what we have. And then we have ui plus 1, that is equal to ui plus h times dou u by dou x plus h square by 2 dou square u by dou x square plus h cube by 6 dou cube u by dou x cube plus h power 4 by 24 4 and so on. Okay, so that's what we have. Then again, by inspection, I can say that I don't need to multiply this with alpha and beta. Rather, all I need to do is basically add these two equations such that essentially this and this will get cancelled and we will have no terms that are of first derivative terms. And then these two will get added up. And then again, these two will get cancelled. And then again, these two will get added up. But however, this is an order h power 4 term. But when we divide with this order h square, this is going to become order h square. So we end up with exactly the same formula that we are looking for, which is second derivative calculation to second order accuracy, right? That's what we're going to end up with. That means I'm going to simply add the equation 1 and 2, which is going to give me on the left-hand side ui minus 1 plus ui plus 1 equals, on the right-hand side, we're going to get 2 times ui plus, we're going to get h square by 2 plus h square by 2. So this is going to be h square dou square u by dou x square. Then plus, this is going to be 0. This is going to be order h power 4. Okay, that means my dou square u by dou x square at I equals ui plus 1 minus 2i plus ui minus 1 divided by h square plus order h square. Okay, so this is the central difference formula for central difference scheme for second derivative to second order accuracy. Okay, so that's what we have. Fine, of course, we can go on deriving these formulae. For example, you can try deriving second derivative dou square u by dou x square at I using central difference scheme to fourth order accuracy. Okay, now as we have mentioned, if you want rth derivative to mth order accuracy, in general, if it is a forward difference or backward difference, then you need r plus m points. Okay, if it is a central difference, if r is odd, you still need r plus m points, right? That is what we noted when we calculated dou u by dou x, right? Whereas when you have central difference scheme, when r is even, then you can get away with r plus m minus 1 points. Okay, but one thing to note here is that in the case of central difference scheme, the rth derivative could be odd or even. However, your m, the order of accuracy, is always even, right? You cannot get odd derivatives for central difference schemes, correct? That is because of the symmetry that is involved. You can verify that. Okay, you can check that. So with this background, then now we can go back and see what will be the stencil for dou square u by dou x square to fourth order accuracy. Our derivative, the derivative is a second order accuracy. Our accuracy, a second derivative. and accuracy is 4. So because this is even derivative, we just need r plus m minus 1 points. So this is going to be 6 minus 1. This is 5 points. That means we would require I plus or minus 1, I plus or minus 2, right? If you can write u at all these 3 points, expand them, and then use values of alpha, beta, gamma, and so on, then you're going to get essentially a scheme for second derivative to fourth order accuracy. Okay, so that is the idea here. Now, one thing to note here is that now let us say if I were to calculate, let us say I am given some function. Okay, let us say this is sine x by x cube or something. So some function is given. Now for this function, I can calculate what is the derivative. I can calculate what is df by dx, right? I can calculate this df by dx at a particular x value, and I can calculate that with either first order accurate scheme or second order accurate scheme or fourth order accurate scheme and so on, right? I can use different schemes to calculate df dx. This is basically nothing but your dou u dou x, right? Okay, we have seen several schemes. Again, we can make use of either forward difference formula or backward difference formula and so on. Now, if this is the case, then to check for order of accuracy of the scheme, so numerically, so we have proved that a particular scheme is second order accurate, first order accurate, fourth order accurate, and so on by looking at what is this order h to the power n. Okay, we said if n is some number, this is going to be nth order accurate. That's what we said. Nth order accurate. But then this is, we are saying from theory, right? From the looking at the equation. But how do you prove that this is nth order accurate? Numerically. So for that, what you can do is essentially you have f of x. Let us say you take a simple function for which the analytical derivative exists. That means you can calculate what is f prime of x. Okay. You can apply UV formula and then calculate this derivative analytically. Okay. I can also calculate this numerically, that is df by dx. And then I calculate the analytical derivative and the numerical derivative at the same location. So I know what is x. At that location, I'm going to calculate these two. And difference of that, these two is going to give me, these two is going to give me the error, right? That is going to be f of x minus df by dx at a particular x. Okay, let's say a particular x value. That is my error. Now, this I have calculated, let us say using a particular delta x or a particular h value, right? That's what I have done. So that means if you go back, we have written dou u by dou x equals ui plus 1 minus ui divided by delta x plus order delta x. As I said, when I reduce my delta x, my df dx accuracy is going to become better, right? Because my delta x becomes half, my truncation error also becomes half, right? But then the analytical value is not going to change. So as a result, my error is also going to decrease, but error is going to decrease because now my numerical derivative, that is df dx, is better because the truncation error has reduced, right? So as a result, my error will decrease because my df dx is now better, okay? But then it is only going to decrease as order delta x. That means if I'm going to look at this equation and relate the error to order delta x, then my error can be written as goes as order delta x, okay? But if I take a higher order accurate scheme, let us say error goes as order delta x square, right? That means if I'm going to take logarithm of error goes as 2 times logarithm of delta x, right? Essentially 2 times logarithm of delta x. That means if I'm going to, let us say, take some values of delta x, let us say delta x could be some values. Let's say this is 10 power 0, 10 power minus 1, minus 2, minus 3, and so on. So I'm refining my delta x, right? Initially, I have taken delta x to be 0.1. After that, I will probably take 0.05, 0.025, and so on. So I can mark those values. And then on the y-axis, I can plot what is the logarithm of error, right? I'm taking logarithm because then it's basically going to give me some kind of a y equal to mx plus c kind of graph. Okay, so then I can mark these points. So I calculate error for 10 power 0 or some h value. Then I reduce the error, then reduce the h, and then I'm going to calculate the error. It's going to become smaller. It's going to become even smaller, and so on, right? So if the scheme were, let us say, some kind of a nth order accurate scheme, second order accurate, this slope will come out to be 2, right? On the other hand, let us say if I have a fourth order accurate scheme, then I start with some error. Then as I reduce my H, this error is going to drop down more, and it's going to drop down more and more, right? That means this slope will be equal to 4, right? Because it is now dropping much more quickly. Similarly, if I take a first order accurate scheme, that will have some error, but then as I reduce my H, it's not going to fall down so much. So that is going to be, the slope of that is going to be only 1, because we only have order delta x as the truncation error in that case, right? So we can, by plotting logarithm of error versus logarithm of H, I'm using logarithms because then the errors and the H are changing in powers, right? Essentially, they're going as H power n, and the error is only also decreasing quite large. So I'm using some kind of a log. Let's say this error is 10 power minus 2, minus 3, minus 4, minus 5, and so on, right? Then I'm going to basically plot this y equals mx, and the slope of that curve is going to basically give me the numerical order or numerical truncation error of that scheme, right? Numerical truncation error of that scheme, right? Theoretically, we have anyway proved it, but numerically, this is how we can show. So we can plot such a curve by simply calculating the function value and then calculating the analytical derivative and then the numerical derivative, that is partial f by partial x at particular grid point xi. And then, of course, repeating this process for different values of delta x, right? Essentially, I take different delta x and then see if my derivative is the error is actually decreasing or not. Okay, so that is how we can, in practice, verify the order of accuracy of a particular scheme. Okay, so you will find that such plots are typical in numerical methods papers. Okay, wherever you see, if people are introducing some kind of a new method, then they must check for the order of accuracy, the numerical order of accuracy, which they will prove by plotting something like this, in addition to proving what is the theoretical order of accuracy. Okay, so you'll find something like that. Okay, so I think we are out of time, so I'm going to stop here unless you have any questions. I will also post your second assignment sometime, maybe tomorrow or so. This will involve problems from the solution to system of or solution to nonlinear equations. Okay, solution to nonlinear equations and the systems. Okay, nonlinear equations. I don't think I have system problems in there. I'll check anyway. So it's a solution to nonlinear equations such as the bisection method, Newton's method, and so on that we have seen. So they again, just like the assignment 1, you will have hand calculations plus programming. Okay, both of them will be there. You'll have hand calculations plus programming, which you can work on and submit. Okay, maybe in a couple of days I'll try to post that through the code office. Okay, guys, I'm going to stop here. So going forward, we'll look at slightly modified version of this particular scheme by tabulating these series coefficients rather than writing them in a series like this, because this will get very cumbersome as we include more and more terms. So we're going to look at a somewhat compact way of presenting or calculating the derivative to a particular certain order of accuracy. So that's what we're going to look at. And then we're going to look at how to calculate truncation error for a given equation and so on. Okay, that is what is coming up for the next lectures. Okay, so then I'm going to stop here. I'll see you guys on coming Monday again.
Hello, sir. Yeah, just one request. Actually, like these are involved like a lot of derivations, and if we can means share us like some kind of a problems like where like we come across like how the results will be through the analytical as well as like through the experimental, if some problem is taken and how this is derived, that would be really helpful for the understanding actually.
No. Can you explain again? So what we are now right now doing is that we are coming up with the scheme. Okay.
Yes.
Yeah. So the scheme is we are using Taylor series expansion to come up with the scheme. Okay. Yes, I didn't get your question. So
these involve like a lot of derivations actually. Like parallelly, like along with the derivations, if we can like show us some kind of a problems, like how means some kind of a problems like in the computation, like we means through ANSYS or something, like we would be like taking some problems and it will just provide us the results, but this will be the background of these things.
Right,
If
right.
if we
So,
take
okay.
some very simple problems, yeah, that would be really helpful actually.
No, the thing is, okay, I think your question is very, I'll explain it. So the thing is, we are not going to use ANSYS or, any software like that, because that is solving a full set of, equations. For example, the solid mechanics equations or the fluid mechanics and so on. That is quite complicated. We are not going to look at anything like using a software as such, okay, in this course. But what we're going to look at is, we can certainly try to solve these things using MATLAB, where, these equations are used, and then you calculate a derivative. For example, just like what we have done in the root finding, you can show the numerical order of accuracy, something like this. Now, let us say you go back to ANSYS tomorrow or today and then see what kind of schemes it has. It says it has a first order accurate scheme, second order accurate scheme, and so on. So those schemes, what it is using are what we have discussed today, right? And numerically, it's going to give, if you're going to evaluate them using a small program, this is how they're going to evaluate. But then, unfortunately, you will not find the order of accuracy evaluation of the scheme in any of these softwares. So they will only use the scheme, but you will not be able to get the order of accuracy from that software as such. Okay. So yeah, I mean, essentially the thing is that now these derivations are important because we are learning how to derive new schemes. Now, some of these schemes may not be available in many of these software because they work with pretty much lower order accurate schemes. But then we are looking at a general method where we can derive these schemes from first principles. Okay. However, we will try to see wherever possible we can, try to include some example problems like the way we have done before. But this chapter, Basics of Finite Difference Method, will contain a lot of derivations as such, because that is the backbone of deriving all these schemes. Well, for simple structured meshes. Okay, we are not even looking at any complicated things in here, right? So for this one, unfortunately, we won't be able to do anything with the existing software as such, because these results are used in the software as a particular scheme, but not these derivations as such.
Okay.
Yeah, but we will try to see if wherever possible, we'll try to draw some, parallels and so on.
Sure, sir. Sure.
Yeah,
Thank you, sir.
But you'll work on some of these things, some of these, order of accuracy calculations and all in your assignments, where you will appreciate how this is coming. Okay.
Sure, sir. Sure. Thank you, sir.
Yeah. Thank you.
Sir, I have a question. So, how many assignments in total we might have, sir, for this? Just for,
maybe. Yeah, sure.
sir.
So we may have how many chapters we have?
5, sir.
Yes, we'll have 5 assignments. Yeah.
Okay, sir. Why? Because for final year we are having project also. Main project is also running.
Sure.
That's
Yeah.
why, sir. That's the reason, sir. Sir, another thing for the exams, we will be asked for the derivations also, or we will be only solving the numericals.
No, you will be asked for derivations also. Yes.
Sure,
Essentially, these derivations, what we are doing.
Okay, sir.
Yeah,
So,
like what we're doing, following the same, set of principles and all. So it should be straightforward. In fact, you should be happy we are doing some derivations in the exam, because those are, easier than actually putting in numbers.
Okay, sir. Okay.
Yeah. Because if you put in numbers, very easily you can get incorrect answers and may lose points.
Understood, sir. But a very selfish question: can that cheat paper which you said we can take, can that be a bit elaborated, sir, so that we can?
Yeah. I'll just think about that. Yeah, I think it can
Please,
be
sir.
maybe. I'll see if I can make it.
Yes, sir. Because in
few pages
thermal, yes, sir. Because in last semester, last semester, we had thermal measurements in engineering. That was also pretty vast subject. So we were given the option for an open book exam. So
Right.
yeah. So if that could be done, to be very honest, sir, it's not. I mean, we basically couldn't that much comprehend to complete these derivations to prepare for the exams per se, sir. In that sense,
Right. No. I'll see if I can make it open notes. I don't mind actually. It can
Yes,
be
sir.
open notes. But only
Yes,
thing
sir.
is that, see, when we go to open notes, the exam gets a little tougher because already all these things. That is the problem.
Sir, okay, sir. Understood,
Yeah.
sir. But,
I mean, see, for
so-
example, let us say we have derived, let's say, second order accuracy formula like this in the class.
Yes,
If it is
sir.
a closed book exam, I can even ask some variant of that. But if it
Okay,
is
sir.
open book
Okay.
exam, then it will become, because you cannot directly ask from what is there in the notes.
Yeah, understood,
Right.
sir.
So
Understood,
it will
sir.
become a little more complicated. I'll see if I can, make an open notes exam or something like that.
If
Okay.
you can just tailor make for us, it'll be very
Yeah.
helpful, sir.
Yeah,
I
yeah,
mean,
sure.
just being very frank in this, sir. Not in any
Yeah,
other
yeah,
sense,
sure. No, it requires some preparation. Okay, you
Yes,
have to
sir.
probably go back and then look at what we're trying to do. And you should,
Yes,
I mean,
sir.
all of you should also ask questions, Yeah, I mean, I can ask you questions, but you should answer. But then you should also ask me a lot of questions. I think,
Yes, sir.
yeah,
Sir, we are actually in kind of a backlog, sir. To be honest, like I have just completed the running the videos until 12th or 13th lecture. So I mean,
Okay.
so that's why like certain doubts are coming in, but ideally that kind of helps out to get sorted out in assignments and other things. So
Sure.
so
Yeah,
it's
yeah.
getting handled out, sir. So
Yeah. So if
thank
you
you,
have
sir.
questions, you need not ask me in the class itself. You can even email me, just put in the questions.
Definitely, sir.
We will
Definitely,
reply
sir.
back to you.
Definitely, sir. That'll
So
be
not a
very
problem.
helpful, sir.
Through
Sure,
the
sir.
portal, you can just put it, and then myself and the TAs are there to answer. Okay. It can be any simple question. I mean, don't worry if it is something that is covered or
sir.
if it looks silly or
Understood,
something.
sir.
It
Understood,
doesn't
sir.
matter, But the important thing is that you should ask questions so that you will clarify doubts.
Thank you so much, sir. That's very helpful,
Okay.
sir. Thank you,
Yeah,
sir.
yeah.
Thank you, sir.
Thank you.
Yes, sir.
Any other questions, anybody? Okay. If not, I'm going to stop here. I'll see you guys, talk to you guys next week. Okay. On Monday.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, everybody. Thank you.
Thank you, sir.
Thank you. Bye-bye.
Thank you, sir.
Thank you.